Yes. My group is studying atmospheric aerosols, which are these tiny particles that are suspended in the air around us. They can be anything from nanometer to micrometer in size. So this is between a millionth and a thousandth of a millimeter. So they're very, very small, and we cannot see them with the naked eye. And they are everywhere around us in a single cubic centimeter of air. So this is the volume roughly of a sugar cube. There can be thousands or even millions of individual particles. And these particles, they come from many, many different sources. Many are natural, so this could be breaking waves, forest fires, dust storms, these are natural, or many man-made processes, mainly combustion of fossil fuels, so that goes into transportation or power production, but also mechanical wear, such as brakes and tires from cars. And finally, the particles can also come from gases that nucleate inside the air. And once these particles are in the air, they can have a number of different effects. And one of the main that we have studied is the impact on climate. We know that particles have a critical contribution to climate change, but at the moment it's the one of those that we understand the least well. Also, the particles are one of the critical elements in the formation of air pollution and how that evolves. And when we inhale particles, they can have a number of very unfortunate impacts on our health. And these are the main reasons that we want to study the properties of these atmospheric aerosols. Okay, so here we produce aerosol particles in the same way that we would do in our lab at home. And then we use the aerosol injection setup to introduce this stream of particles into the measurement chamber where it can interact with the X-ray pulses. And so when the particles meet the X-ray pulse, the light is scattered, and we collect the scattered light, and from this we can construct a diffraction image. So the key here is that the X-ray pulses are so intense, which means that we get so many photons in a small area for each pulse that we only need a single hit of a particle to construct such a diffraction image. And this is only possible at free electron lasers. And in addition, here, the number of pulses that we get each second is so high that we can collect many, many diffraction images from single particles. The amount of images that we have collected in the last days, so less than a week, would other places take many months to collect. And this means that we get excellent statistics for our investigations. So we use single particle diffraction imaging to study the size and the morphology, the shape of individual aerosol particles. When we hit an aerosol particle with the X-rays, light is scattered, and we collect this light to form a diffraction image, which we can transform into an actual image of each individual particle. And we want to study how these sizes and shapes vary across a population of aerosol particles, so all the different particles that are in a larger volume of air. Yeah. So normally, when we connect our aerosol experiments to theory or models for their effects, we have to make a number of assumptions about the aerosols that we produce. One of the things that we have to assume, because we have had no other option until now, is that the distribution of aerosols that we produce is stable. Another thing we very often assume is that all of the particles of all the different sizes have the same shape. But when we start to look at aerosol particles that more closely resemble the very, very complex aerosols that are out in the real atmosphere, then this becomes more questionable. So this affects how we construct our theories and models, and ultimately it will affect what effects we can predict with these models of real aerosol out in the atmosphere. So their climate effects, their impacts on air pollution, and their impacts on health of inhaling them. So these experiments we have done now will probably change how we look at the aerosol we make in the lab, and this has the potential to change our theory and our models on several of the key properties that we are investigating in lab experiments.